My name is Maxleene. This afternoon, I'm going to give you a presentation where I'll provide a very basic introduction to multivariate data analysis, which is a way of finding meaning in metabolomics data sets. So the presentation is in two parts where I have a few slides just to introduce the basic theory. And then at the end of the presentation, I'm going to do a step-by-step demonstration on two of the methods that we normally use when we do plant metabolomics in our research group, which is the Phytomedicine research group. Okay, in this slide, I want to introduce multivariate data analysis. I have two definitions that speak to the term multivariate data analysis, where the first one highlights the use of statistical methods to analyze data that is generated from more than one variable. We are well aware, I think even from this morning's talks, that data is generated in different forms. We have univariate, where there's one variable, and then we have bivariate as well. And our main focus for this afternoon is analyzing multivariate data, where we have more than two variables. The second definition, which looks at, once again, many variables, which is multiple variables that are analyzed simultaneously to understand the relationships that may exist between them. I think we agree that nowadays, big data is being generated in most laboratories, and this is mainly because of the sophisticated instrumentation that is available and also the availability of software to handle big data. In line with multivariate data analysis, we often hear the word chemometrics. I think Velma was talking about it this morning, and we wonder what is the relationship between the two. So multivariate analysis of chemical data is chemometrics, but looking at the definition of Hopke from 2003, it states that chemometrics is a chemical discipline of extracting information from large chemical data sets. And this is by the means of mathematical and statistical algorithms. Just once again, illustrating that there's generation of large data sets, and then we use the statistical and mathematical algorithms. Recently, there has been an emergence of a new term, which is called biochemometrics. Biochemometrics, although I didn't put the definition here, it simply just uses chemometrics to analyze chemical data and try and correlate this to biological effects or biological activity. This is something that is also quite often used these days. So the importance of multivariate data analysis lies in its ability to convert numerical data into meaningful information. Most of us researchers, when we do our analysis, we produce a lot of numerical data, which is the big data, and there's no useful information until there's some kind of analysis. And this is now made possible by the use of different types of software. The common one, which I'm going to present this afternoon, is Simca from Umetrics, and then Unscrambler, which is also a licensed software. And then we have the online softwares, Metabolomics, which was discussed this morning, and another one called BioStatFlow. I'm sure there's many others that I haven't mentioned, but these are the ones that I could just remember from the top of my head. So depending on the research question that the researcher has, there are different types of multivariate data analysis that can be done. There is exploratory multivariate data analysis, which is quite common and which is quite popular, where you just want to look at an overview of the data. You want to see what are the patterns in your data. Are there any trends or any groupings? This can be in phytochemistry or metabolomics involving other in vivo systems. So this is applicable to a lot of situations. And then we also have the classification method, where we are the objective of identifying classes, where the classes might be existing classes, or you want to be able to analyze new classes. And then the third type of multivariate data analysis is calibrations, and calibrations are usually done so that we can predict future events depending on the setup on the system that you're working on. Okay, there are various methods that exist that are applied to multivariate data analysis. And this depends really on the research question, and it depends on the output that you want. So principal component analysis is one very common one, which is an exploratory method, or cluster analysis method, which seeks to just get an overview of the data sets that you have. There are other methods like hierarchical cluster analysis as well, which works hand in hand with PCA analysis. Then we have orthogonal projections to latent structures, and this is a classification method that is mostly used when you want to define classes and see what are the variables that are responsible for the differentiation of the classes. And then we have partial least squares, which is a classification method, but also normally used for calibration if it is partial least squares regression analysis. Okay, in this, in the demonstration that I'm going to perform a little later on, I'm going to focus on principal component analysis and OPLS as overview methods. So what is principal component analysis? This is an unsupervised maximum variance method, which seeks to analyze variance within a data and then plots it onto graphs, or making it easy for us to analyze so we can see it visually on plots. PCA converts data tables to pictures. And this is just to simplify things for us because we have big data that we need to be able to visualize. It is exploratory, I've already mentioned this, and provides you with overviews and reveals patterns in your data set. So the principle really, principal component analysis is that it reduces the dimensionality of your large data that you would have gathered from your instrumentation. And this it does by transforming the large set of variables to smaller ones on a new coordinate system. And then while it's doing this, it minimizes the loss of information. Okay, so there's generation of a new coordinate system where the direction of maximum variance in your data lies in the first coordinate. And then there's so many other coordinates that are formed in the PCA, but as the number of coordinates increases, then the importance of these reduces because the variance also reduces as it models the data. So there's certain notation that is used in PCA. This is common, I think, in most software, where when you put your data in the software, N refers to the observations, which are the samples that you're analyzing. This is just so that when we start doing the demonstration, we are well aware of what is happening there. And then K represents the variables, which can be your retention time if you have your chromatography data, or wavelengths or wave numbers if you have your spectroscopy data. And then there is PCs, which refers to the principal component. And this is, like I said, there's a new coordinate system that is generated. So we will look at PCs with regards to that system. And then A refers to the number of PCs. This is very important when you want to do the model diagnostics. You can't just plot any number of PCs. You need to optimize these. So in this new coordinate system, we are going to come across T1s, T2s, up to so many Ts, and these are the scores which are related to your observations or the samples. And then we also have P1, P2, and so forth, which are the loadings which are related to your variables. So in PCA, once we have modeled, there are two very important plots that allow you to be able to visualize your data, to be able to interpret it quite easily. And the first one is the scores plot. And I'm sure from the previous slide, you can tell that scores is related to mapping of your samples. So this is in relation to the diagnostics of your observations. So you're able to view your samples, their distribution in 2-dimension or in 3-dimension, and you are able to see if there are any outliers in terms of the chemical profiles or metabolite profiles. And yeah, and try and see if there's any groupings and anything interesting that you might want to investigate further. The second plot is your loadings plot, which is your map of the variables. And the variables in this case, then you can see the correlation between these, and the loadings plot also allows you to correlate your variables to your observations or your samples, in a sense that you know if this variable maybe is high, then is in a certain position, then it means, which corresponds to your observations in the score plot, then it means that there is a correlation between that variable and those samples. So PCA model diagnostics, this is something that is very important because Once you have developed your model, you need to know if it's making sense. And the diagnostics that we use are, the very first one is your goodness of fit, or your fit, which is your R-squared. This has to be as high as possible. The maximum you can go to is 1. And a good model is usually represented by an R-squared of 0.5. But then again, it also depends on the type of question, excuse me, on the type of question, and also the type of data and the type of model. If it's calibrations, the higher the R-squared, the better. So you want a calibration model of 0.9. If you are doing PCA and then you get 0.5, that is also good, because there is also so much that you can do with principal component analysis. Okay, and then we also look at the goodness of prediction, which is your Q-squared, and this value is determined through cross-validation. Once again, the higher the better. So you want your model to have a good prediction ability, so that if you're going to bring in new samples, the prediction has to be good. So the higher the better, 0.5 and going onwards. Okay. Another parameter that I just put in here is not necessarily a diagnostic, but you need to determine the optimum number of components to avoid overfitting or underfitting your model. This is very important, because our softwares, they tend to give us the freedom to auto-fit and freedom to just leave the software to do everything by itself. So you need to be able to go in and see if your model makes sense, if it has been overfitted or underfitted. And for you to be able to do that, usually with PCA, you look at the R-squared and the Q-squared of each component. The Q-squared is very important. It determines whether your model is overfitted. The Q-squared goes high, it increases from PC1 or from T1 going up. And when it starts plateauing, or when it starts decreasing, that's when you know that I'm probably overfitting the model. I've reached the optimal number of PCs and I need to stop. This will make more sense when we actually do the demonstration. Very important in principal component analysis or in multivariate data analysis, it's data pre-processing. There are different ways that the data is pre-processed. There's transformations, centering, scaling, and signal correction methods, which are also called spectral filtering methods. Transformations, these were mentioned this morning, that if your data is not normalized, then you can normalize this. You can do log transformations and so forth. This helps to make your model make more sense. Then we have scaling, which adjusts large variance within the data. So your variables that are probably within different ranges, they need to be adjusted for that large variance so that everything makes sense. This is something that is very commonly used in PCA, and PCA is scale dependent. So you need to scale your data. If you don't scale your data, then you may struggle to actually observe outliers. So there are different scaling methods, and selecting the best method is not an easy task. However, there are some methods that have been used, and most researchers will probably attest to their efficacy or to their significance. So we have unit variance scaling and center scaling, Pareto scaling, and no scaling. Those are the 4 common ones. So what is unit variance? In unit variance, your variables are given equal weight. And by application of mathematical and statistical equations, the data or the variable is divided by the standard deviation so that the variance is 1 for the variables. Center scaling, the average mean of each variable is subtracted from the variables. And then Pareto scaling, which is the one that's very common. In this case, we are dividing each variable by the square root of the standard deviation. This is the difference between Pareto scaling and unit variance scaling. Unit variance divides by the standard deviation, and Pareto scaling uses the square root of the standard deviation, which results in data that is spatially intact, which is closer to your original measurements. And this is why a lot of researchers would go for Pareto scaling and not unit or center scaling. But however, this really is data dependent, depending on the nature of data that you're analyzing. Most resources do not recommend UV scaling for spectroscopy data. because you want to bring all the variance to an average of 1. And then Pareto, being an intermediate of the UV and center scaling, is commonly used in metabolomics. So this is just an illustration from the Umetrics reference that I have. It's just comparing the 3 types of scaling that I've just mentioned, where the 4th one, non-scaling, means that the data has not been scaled. So in this case, when you look at center scaling, this is what your NMR spectrum looks with center scaling. And when you've done Pareto scaling, it looks like that. And when you do UV scaling, it looks like that. So the choice is yours. Which one is closer to your original data? And then although multivariate data analysis allows you to do a lot of manipulation, it's important that you try and maintain the integrity of your data. Otherwise, you lose information or you start modeling noise, and then everything just goes out the window. So the second example here is also for a mass spectrum, where here there is no scaling, and here there is Pareto scaling, and here there is UV scaling. Okay, so once again, it's important to see what the scaling method does to your data, and then you can make an informed decision. The other type of data pre-processing is spectral filtering or spectral filter signal correction, where once again, mathematical equations are applied on spectral data to reduce physical effects and enhance information. Spectral filtering is usually applied to your infrared spectroscopy data. That's your MIR, NIR, and NMR maybe as well. So the physical effects that we need to remove from this spectra is because sometimes we analyze powders or liquids, and then there are light scattering effects, then there's particle size interference or differences, and then it leads to variations in your spectra. And this is not something that you want to build into your model, because your model, say in the case of plant metabolomics, needs to be built based specifically on the chemical profiles and not any other physical interference or physical effects. So spectral filtering improves your model performance. We will see this in the demonstration. Sometimes when you have a low R squared or your Q squared is low, and then you apply spectral filters, then you can see that the model improves, and also the patterns or the groupings in your samples, they become more pronounced when you apply spectral filters, as long as it does not distort the original data. So I've listed here the different types of spectral filters, where we have multiplicative scatter correction, which we denote as MSC, and then we also have standard normal variate, which is also denoted as SNV. The two eliminate light scattering, and usually they are used interchangeably because they yield more or less the same result, where the effects of particle size variation are actually eliminated. However, the mathematical equation that is applied for the both of them is different, and which brings about that small variation. And then we have orthogonal signal correction. This you will see when we look at OPLS, it reduces interferences in your spectrum or in your data that are not correlated to a Y variable, because when you introduce your Y variable in orthogonal methods, you now just want to look at data that is only related to your X and your Y. Okay. Derivatives, we have first and second derivatives, and these reduce peak overlap and they remove constant baseline drift, which is the first one, and then the second one will remove linear baseline drift. However, when you use derivative, you tend to introduce a lot of noise. So this is also something that just to keep at the back of your mind, you need to look at your spectra before you derivatize, and then after you derivatize, and then you see if you have not lost information or you have not introduced too much noise, so that you end up with a model that will not give you a good prediction. Okay, so that was just an overview of principal component analysis. The other method that we are going to just briefly look at is orthogonal projections to latent structures analysis. Specifically because this is a classification method, usually it is an extension of, say, OPLS discriminant analysis, because we want to discriminate between classes. So the major difference between PCA and OPLS is that OPLS is a supervised maximum separation method. So here we're looking at maximum separation, and yet in PCA we're looking at maximum variance. Okay, so the method is supervised in the sense that we have predefined groups, or we have information that we already know about the data, and then we introduce this into the model, and we want the model to be able we want our software to be able to model the X matrix based on the classification that we have introduced. Okay. So the method is used for classification and discriminant analysis, as I've mentioned, and this is a modification of the PLS algorithm. So PLS, as I mentioned previously, it can also be used for classifications where it becomes PLS discriminant analysis, and the modification of this where they introduced the orthogonal component then resulted in what is called OPLS DA. And this modification was performed to improve the interpretation and reduce the model complexity. You will see this in the demonstration. So what does OPLS do? OPLS modeling separates your X data matrix into data that is correlated to a Y variable which you introduce, the classification that you've introduced. So it tries to correlate in the predictive variation, it correlates variation between X and Y. And then we have orthogonal, which is systematic variation, which has nothing to do with the classification that you have introduced. So that one is uncorrelated variation between X and Y. So it seeks to separate the two so that you can have useful information related to the class separation. And then it also is able to then look at the non-correlated data, and then you can analyze it separately to see what information is contained in there. So the notation for OPLS is almost similar to PCA, where once again, N is the observations or the samples. We have K as the X variables, which is your chromatography or spectroscopy data. And then we now have an M, which is your Y variables. And this is like your class information or your treatments that you are going to assign. And then we have TP, which is the predictive scores, TO, which is the orthogonal scores, and then P, predictive X loadings, and P orthogonal, which is your orthogonal X loadings. The plots that we will come across in OPLS, we have the scores plot and the loadings plot, which is similar to what we observed in the PCA. However, in the scores plot now, we are able to see a rotation which separates your, where your T1 always looks at the predictive information in your X data matrix. And then T2 going forward will depend on the number of classes that you would have applied, assigned. And then we have the loadings plot once again, which shows variables correlated to class separation. And then we have an additional plot, which is the S plot. An S plot in this case is only applicable to two groups. So if you have two groups or two classes that you've assigned, then you're able to use an S plot, where it shows you variables that are correlated to class separation. More than two groups, you are not able to use an S plot. Therefore, you refer to a loadings plot. Okay, very important, all classification models must be validated. In essence, whatever model that you get with PLS or with OPLS, you have to validate it or you have to test it, which means you must bring in external samples that you already know information about, and your model should be able to verify this, and that will give you sort of an idea of whether your model actually works or not. Here I'm just demonstrating the S plot, which I think a lot of us usually struggle with, to know when do you stop when you're selecting your biomarkers or your chemical markers that are responsible for variation in a data set. So this is adopted from Cohen, the metrics reference that I used, where your S, the shape of the variables, they assume an S if you're working with two groups. So the variables that you find in the top S end of the plot, these ones will be, they have low risk of fake or spurious correlations. So these are the ones that we normally use as biomarkers. And then also the ones that are at the lower S of the plot, There are also low risk, so these are selected. And once you start moving towards the center, then there's a high risk of fake correlations, and then we must try and avoid this region when you're selecting variables or biomarkers after you've done your S-plot. So just to give you a general workflow that we follow here when we do our plant metabolomics, and some of this has already been explained in detail. We do the sample preparation. Velma explained this very nicely in the previous talk. And then there is data acquisition, which can be LCMS, GCMS, or any of the spectroscopy methods. And then once we obtain this data, in the example that I will show, we're going to use LCMS data. So once we obtain this data, the chromatograms, we need to pre-process the data to generate a data matrix, which we are able to use in the software that we are working with. In our case, we use Maxleene software to be able to pre-process LCMS or GCMS data. I believe these softwares are instrument specific. So probably people that are using a different instrument, LCMS, which is not Waters, will have a different software to pre-process their data. And then in terms of spectroscopy data, the spectra are just exported from say Opus or Nearcal, and then you put them into Microsoft Excel, and then you're able to generate your data matrix. And then you can add more information depending on the kind of objective that you want to achieve before you actually export the data into the software. Okay, and then following that, you then do principal component analysis for your cluster analysis or exploratory methods. And then you can do PLS or PLSDA for your classification analysis. Just something to mention here, usually whether you're doing PLS or PLSDA, PCA is the first step in multivariate data analysis because it just gives you an overview of what is happening in your data. And you're bound to pick up if there's any problems, you're bound to pick them up in PCA before you even proceed to do any other special kind of supervision, if I can say that. So in the next slide, I'm just showing you just a brief overview of step 2, which is the data pre-processing. This is what happens in Maxleene. This is LCMS data. So what we have here is samples that we ran on the LCMS, and then we want to analyze, say, for instance, these few samples that are highlighted here. So you just highlight them and you inspect the chromatograms, and then this is in Maxleene software, and then you need to come up with a method. So you edit a method, okay? And what does the method do? What is the purpose of this? The purpose of doing pre-processing is you want to do spectral alignment. Your LCMS data, you want to see the differences between the chromatograms in an untargeted approach. So for instance, you want to use your whole chromatogram. Maybe you're using high performance chromatography and you have your chromatogram starting at 0.75 minutes and ending at 7.75. So you want to tell the software that I want to include all the information when I do the SIMCA, the chemometrics. So you need to put in these parameters for peak detection. You need to identify your low and your high masses. So all of this needs to be done while you're inspecting your chromatograms of your samples. You can pick a few and then just to give you an idea of what is going on in your data set. So all the parameters are actually entered in. You need to determine your peak width at 5% height. And you need to determine if you're going to apply smoothing or you're going to lose information. Very important is to determine your marker intensity threshold. So you look at the smallest peak and then you take that value, and then what you need to put in as your marker intensity threshold has to be something that is lower. And then you need to eliminate noise in your chromatograms. So your noise elimination level is extremely important. And this varies obviously from data sets and from what you are analyzing. If you put a noise threshold that is too high, you're going to lose some of your peaks. So you need to inspect your chromatograms before you put all of this information in. And then once you've done that, and then you can do your spectral alignment. The software runs everything, and then you generate a spreadsheet that looks like this, which is your data matrix. So in this spreadsheet, in terms of LCMS, you have your retention time, and your mass charge. So this pair is a retention mass charge pair. And then these two columns, retention time and mass charge, and then we have columns going the other way. These are your samples. Okay, and the readings here, your data matrix comprises the intensity of each of these pairs. So this is what we're varying, and then this is what we want to analyze in our data set. So we run large sample sets, sometimes over 300 samples. So clearly you can see why we then need multivariate data analysis, because you can't go in and look at these samples one at a time. So you need some kind of software that is able to do this for you. Okay, I will now demonstrate principal component analysis in simpler software, and then I'll also show you OPLS. I will bring up the software. Well, are we okay?
Yes, we're good. Good.
Thank you. Okay, so this is a spreadsheet that was generated in Maxleene, where we analyzed various types of ginsengs, commercial ginsengs that are used for different purposes, and we just wanted to see how are these ginsengs different. If everything is called ginseng, are they really chemically similar, or they are distinct? So this is your sample ID, which is your primary observation ID. This is what you need to assign. A primary ID has to be unique. If you apply two similar IDs, then the software is going to have a problem. So primary observation ID has to be unique. And then the secondary ID, which is this one, you have to assign if you have, for instance, we know in this case that we had different species of ginseng. So we went in and then we assigned a secondary ID to each of these samples. Okay, your primary variable has to be unique, and you assign it here. In our case, LCMS, the raw data that you generate in that matrix that I just showed you previously, these variables are not unique. The retention time will be repeated the moment we have a different mass charge that occurs at that retention time. The same applies to your mass charge. So we had to come up with say dummy variables, or just to generate automatic variables that are linked to each and every one of these pairs. So that's why you see 1, 2, 3, 4, 5, but this is just something that we automatically generated. The most important variables are these, and we assign them as secondary variables. Okay, once you have your spreadsheet like this, and then you can click on finish. And then you save. You do not exclude anything at this point. Okay. So when you have a data set that only has X variables, the default model that comes is a PCA of X, because there are no Y variables, okay? But it's not fitted, but this is where we are. Something very nice about SIMCA is that it gives you an analysis advisor window, which is this one. So if you click here, it disappears. If you click there, it appears. Okay, so in essence, the analysis advisor just tells you, it helps you with the interpretation of everything that is happening in your plot. I will just remove it for now. And then let me fit this model, the PCA model. So we auto fit. Okay. Once you've auto fitted your PCA model, this is what you get, where the green bar is your R squared X, your blue bar is your Q squared. So this is cumulative variation in your X. So the new coordinate system, we are modeling your variables here. And then in the first principal component, we've modeled so much. In the second and third, this is cumulative, okay? So it can even go up to 1, as you can see. All of this is indicated here. This is where you get your information about your model. Okay, if I double click on there, this is what it shows you. So we have at the moment 11 principal components. The first component model 0.43 of your data. And then the second, so it goes lower and lower and lower, and then until you start modeling noise. And this is the cumulative value, which can go up to 1. It doesn't matter. It will still model noise until you decide on the optimum based on your Q squared, which is this one, which also increases cumulatively as you add your number of components. Okay. So the first and most important thing is to determine the optimum number of pieces. This is too many components. We can see that the model is overfitted, R squared X of 1 and the predictive ability of 1. This would be very nice if the model was not overfitted, but how do we see that the model is overfitted? I mentioned that Q squared bar must increase all the time. Once it starts plateauing, then you know that there's probably some overfitting here. So this is something that you then have to decide on your own. Where do you see plateauing visually, or if you want, you can look at the parameters I just showed you previously. In this case, I am going to stop my modeling at component number 5. So we have to remove the rest of the components. As you remove these, you see that your R squared value will start decreasing and your Q squared will start decreasing. Okay, and you remove them using this icon here. Okay, we have 5 components. In the one resource, it actually recommends that between 2 and 5 principal components are the optimum. Anything more than that, you start modeling noise. So it's no longer chemical data that we're modeling, but just noise. Okay, so we've modeled 0.925, which is 92.5% of your chemical data in the data set. And the predictive ability is 0.9, which is 90.3%. This is quite good. We've used 5 components. I told you A is 5, and we have 36 samples. Okay. Now we want to get an overview of the data. So we look at the scores plot, the scores scatter plot. This is the 2-dimensional, and this is the 3-dimensional. Most publications, they use the 2-dimensional scores plot, which is this one. So just by looking at this, you can see that you have groupings in your data set. So these are the observations, these are your samples. This is what we ran on the instrument, and it is separated based on the chemistry of the LC-MS. Okay, so the highest separation that we are seeing will lie along the first principal component, which is 43%. And what are the clusters that are being separated? Is the one on the positive axis and these on the negative axis. Okay, so at this point, we don't know much about the samples, but of course we have information that the secondary information that we put in. Okay, but we can look at that later. So this is your raw data, and it's important to scale data. Like I mentioned, you can try out different scaling methods. I'm just going to show you how to do one, and I'll create a new model so that I can leave the original model here. So you go to New as Model. This work set shows you an overview of your data. How many variables do you have? 1,953 data points from LC-MS. Observations, you have 36 samples. And then we want to scale our data. So you go to scaling, you select everything. The default is always UV scaling, so you can change it, or you can. So clearly the first model that we have is a UV scaled method. And now we want to change this to Pareto scaling, and then we set. So UV changes now to Pareto scaling, and our model is still the Pca model, and then okay. We don't want to eliminate anything. And then we auto fit again. We remove our components. I think this time I will end at component 5 once again. Okay, so we can see that our model has improved a little bit, 0.969 compared to the original without scaling, and also the Q squared has also improved. So you can try the other two methods as well. But now what we want to see, what does the scaling do to our data, our sample, the relationship within our samples. Okay, we still see separation, and now it's actually more, there's marked separation, and the variation along the first component is now 47.7. This set of samples was sitting on the right, now it's on the left, but still the separation is clear. And it's interesting that we can see the separation also between these two is actually more clearer now. Okay, so this is the sort of information that you get with principal component analysis. And when you look at the scores plot, it's direction of maximum variance in your data set. Now, I just want us to look at, this is PC, the first component versus the second component. You are able to plot the first component versus the PC1 versus PC3. So in this case, now we are also seeing what's happening in the third dimension. We can see the separation, more separation of your samples, but how much variation is in the third dimension is low. It's actually 16.4. Okay, so the most important component will be the first component, and then the second one, and then you can go on until you look at all 5 components and to see how your you can plot component 2 and component 3 and so forth and so forth. Okay, another way of viewing all your data is to use the 3-dimensional score plot. Okay, so your 3D score plot shows you T1, T2, and T3, X, Y, and Z. So in this case, you can rotate the score plot to see the relationship of your samples in space. And then you can decide which of these, the spatial distribution makes sense. Okay, I think most scientific publications, they prefer the data to be shown in 2-dimension, because I think for some reason then the 3-dimensional space is almost manipulative. If I want samples to sit on top of each other, I will present it like this, and it'll make it seem as if there's variation in that direction, or I can separate them like this. But with 2-dimensional, everything, yeah, if you plot T3 versus T2, it sits like that, and then you can see your direction of maximum variance. Okay. So something that we can do with this plot is to change the T1 versus T2. You can change it here, or you can use the keys, the arrows on your keyboard. So I'm going to change this back to T1 versus T2 under properties, and then you just say apply. So now your samples, they've rearranged now. They are sitting with the three groups or the 3 classes. And then we can also color our samples. Now we want to have a little bit of information as to the identifiers that we used. We used secondary IDs where I said we got samples that were Panax ginseng, and then Panax American ginseng, and so forth, pseudo ginseng. So I want to see how these samples sit in this score plot. So you can color these by identifiers, which is the species here, and they will be colored according to that. So you apply, and then you say, okay. So without manipulating the data, you can see that this species, which is ginseng, but belongs to a different genus, is very different from, for instance, Panax pseudo ginseng, while the other 2 ginsengs, which is your Panax ginseng and your Panax fungifolius, are more closely related. So you can then go back to your chromatographic data and actually look at the chromatograms and see if all of this makes sense. Okay, but let's look at the loadings plot, because now we want to see the relationship between the loadings. So you come here, you plot your loadings. Okay, so these are your variables. I'm going to go to properties and label them. Using retention time. Okay, so this is the sort of distribution that you have. in a quadrant, variables that occur in that quadrant are correlated and vice versa, okay? But what is more interesting for me or for most people would be to see the relationship between your variables and your samples. So I'm just going to close these two windows and I will leave the score plot and the loadings plot, but I want to view them next to each other. So I'll tile them vertically like this. So your scores plot shows you your observations in samples, and this shows you the variables. So the correlation here is that samples that are sitting in this third quadrant are correlated to variables in this third quadrant, but it's not all of them. Remember, we talked about fake correlations as you're approaching the origin. So the ones that are here on the outskirts, the extreme ends, have a high probability, have low risk of fake correlations. And then for this group of samples, we look at the variables here, and then for that group of samples, we look at the variables there. So that's the correlation that we are talking about. You can confirm this by selecting a few samples from the one cluster, going on to the chromatograms, and then you see if the signals that are at these retention times are markers or are occurring in high amounts. And then you can do the same here, and then you can do the same there, just so that you get an overview of your results. Okay. So what you report for PCA, you will report the scores plot with you can color it according to what you like. You can also label it according to species if you like. You can change all of that. And then we also report on the loadings plot because we want to see the correlation of your variables and also the correlation of your variables against your observations. Okay. You report on the number of components that you've used, the number of samples, yes, and then you also report on your cumulative variation that you've modeled with 5 components, and then you also report on your Q-squared, which is the predictive ability of your model. Okay, so this is what you do in a nutshell in PCA. There are other plots. Okay, something else to mention on a scores plot. I did mention that scores plots will also show you if you have any outliers in your data set. Fortunately, in this case, we don't have outliers for the purposes of this demonstration, but it would have been nice to get an outlier. So you might get a sample that is sitting here outside of model boundary. What does that mean? It means that the chemistry of these samples in here is almost similar, although there's variation, which is explained by certain percentages. But when you have an outlier that sits outside, it can be a strong outlier, which will skew your model, or a moderate outlier, which you also have to investigate. Outliers essentially point out to a difference or a variation in the profile, which could be something that went wrong with your extraction, or you contaminated your sample, or you went and you got a different sample from what you're actually intending to. So outliers, you don't just remove them from the data set, you have to investigate them. It's important to go back to your raw data, to your original chromatogram, to see why that one sample is different from the rest. If nothing else is wrong, and then it's just an outlier, depending on the research objective. If the objective is to just monitor variation in your data set, it's important to report that you will get situations where some of your samples have a chemistry that is completely different from the rest of your samples. Okay, so we also have other plots. I won't be able to cover everything, otherwise I do not have enough time. We also have other plots, which is your D mod X. D mod X just looks at, it shows you outliers, moderate outliers, defines your critical limit, and then samples that will sit far away from your critical limit as outliers that may need to be investigated, but usually it means that they are moderate outliers and usually have no influence in terms of skewing your model. So you leave them in, okay? And this is just your contributions plot. Okay. Spectral filters. I will show you It's where you find them, but this is not applicable to LCMS data. Like I said, if we're analyzing spectral data, then we'd use spectral filters. So once you have your model, you go to data and then spectral filters. There's a list of spectral filters, and then you choose which one you want to apply to your data, and then the model is going to be rebuilt again after applying spectral filters, and then you have to scale your data again. Okay, sometimes you end up with a lot of models. One last thing that I can just show you on PCA, you end up with many models because you're doing a lot of things. Here I've just shown you two. So it's important to label them, because 2 years from now, when you are now graduating for your master's, you may want to come back and change a plot or something, and you won't remember what model was scaled and which scaling method was used. So if you right click, you can go to change model title, and you can write here original, and then you keep that. And then the second one, you can just right click, and then you write Pareto, for instance, and then you save that, so that at least they're easy to identify at a later stage. Okay, so this is basically it. The analysis advisor I showed you, it's like if you get stuck and you don't know what's going on with a plot, you click on the analysis advisor, which it may not come up for all your plots, but for the important ones, it will come up, and it explains to you what is a score plot, what is it showing, what is the direction of maximum variance, and what do you report. Okay, so that is your principal component analysis. I will quickly show you the OPLS-TA. I'll stop sharing this one. Okay, I've used a different example to illustrate OPLS. In this case, once again, this is LCMS data. We can do exactly the same with GCMS. The pre-processing is the same, and then you just bring in your data metrics into Simca software by you bring in a new project, and then it comes, you import it into the software. Okay, once again, in this case, we have samples numbered 1 up to, I will check how many we have. And this is your primary observation. We have a secondary observation. In this case, we had one plant species that we picked from different provinces. So you will see that the province will differ here. Otherwise, yes, one plant species. And then the additional Y variables that we have put in, which is the classification that we use to supervise the model, is the fact that we know what samples come from which region. So depending on your scenario, you can have a classification based on the sample, the species. In the previous example, we could have used 4 classes where the one ginseng is given a class and then another one, another class. You can use treatments, or in terms of biological activity, the active samples can be assigned a class of 1, the non-active samples can be assigned a class of 2, so that you can correlate the chemical profiles to the biological activity that you're observing. Okay, now in this case, we want to be able to correlate the chemical profiles to the geographical location of the samples of the plants. So once again, we have our primary variable ID, we have the secondary, which is your retention time, and then your mass charge ratio. And then we go to finish. And we save our project. We do not remove anything at this point. Okay. The default in this case is a peerless unfitted model. Why? Because we now have X variables and the Y variable that we introduced. However, like I said initially, with any kind of multivariate data analysis that you want to do, you must first of all do a PCA so that you have an overview of what your data is like. So how do you then change from PLS to PCA? If you double click and then you go to the work set, which is what I showed you previously, this overview. It shows you that we have X variables and we have a Y variable, which is the class. If you select the class and then you exclude it from your data set temporarily, then your model type will change automatically to PCA, and then you can model the data. We don't remove any terms yet. Okay, we now have a PCA unfitted model, and then we auto-fit initially before we can do any scaling or any kind of transformation. In this case, we had 253 observations, which are the samples that we picked from the different provinces. Sometimes if the data set is very large, it takes a bit of time to do the modeling. So we just have to be patient. Okay, auto-fitting, you can see that this is not an X compared to the previous model. This is not as good as the previous one. However, the most important thing and the first thing you need to do is to look at your Q squared. It's going up, suddenly it goes down. That means here you start overfitting, you're modeling noise. So we only need 3 components, and then we remove the rest. Your R squared is going down. Your Q squared is also going down. Okay, with 3 components, we've managed to model 15.4% of all the chemical data and 11.4% predictive ability. Okay, we need to scale the data again, so we can double click, go to the workset again, go to scaling, select all the variables, and then scale them to Pareto scaling. Because we are going to do, so here it's just telling me that it's going to refit the same model because I didn't ask to make a new model. So it's just going to change the existing one. Because we want to do an OPLSDA, OPLSDA only allows Pareto and center scaling. It will not analyze, you will not be able to plot an S-plot, for instance, if you have UV scaling. So Pareto scaling is usually used. And then we auto-fit. You have an option to add only the first 2 components, just so that you can plot T1 versus T2, and then you add, if you say 2 first, you're adding only the first 2 components, and then you can add manually an additional component after another, and then you're still able to see if you're overfitting your model or not. In this case, I will stop at component number 4, because component number 5 is overfitted. Okay, and then we plot the scores plot, and this is one species, and we have samples distributed everywhere. We don't have outliers, strong outliers, moderate outliers. So, okay, we are happy that we have one batch of nice samples, but the objective, we can label this according to the provinces. We can color them according to the provinces, which is the secondary identifier that we use. You can apply and then we say, okay. Okay, So in this case, just by doing principal component analysis, you can see that your Northern Cape samples seem to be chemically similar because they form a tight cluster here. However, Western Cape samples are more spread in your scores plot. Okay, so but now we need to go further and supervise this model and feed this information into the model so that it really shows us the variables that are separating Northern Cape samples from Western Cape samples. Okay, so what do? We create a new model. We look at our variables. We had a class that we excluded, but now we need that class to be back in so that we can have an OPLS model, not a PCA model. Okay, so now we are going to have an OPLS. We can look at our data, it's scaled data, and then we just say, okay. And we are not removing. Okay, so this is the OPLS model and it's unfitted. Okay, I will auto fit. Okay, auto fitting the model, we have 1 plus 3 components, which is 4, number of samples, and these remain exactly the same. We now have a R squared Y, which is also high. So why is this different from remember we said in OPLS, we have our X data matrix has now been decomposed or split into variation, which is related to the classes that we prepared, we assigned, which is your Y. And then we have other variation that has nothing to do with Northern Cape and Western Cape provinces. Okay, if you double click here, it shows you that in this model, this is the cumulative variation in the data. We've modeled 35.6% of the data. But the data that is related to separating Northern Cape samples from Western Cape samples is 12%. The rest is orthogonal, which means it is within group or within class variation. And I think we'll be able to see that more clearly. So OPLS, there is no chance of overfitting usually. The Q squared goes high, and our interest really in this case is the predictive component, which is the component 1, and then it's going to be plotted against the first orthogonal component. A rule of thumb, when you do OPLS, depending on the number of classes that you assign, the predictive components that you'll get is going to be n minus 1. So here we assigned 2 classes, so we're going to have 1 predictive component. If you assign 4 classes, you're going to get 3 predictive components, n minus 1. Okay, now we look at our scores plot. So this is the OPLS scores plot. We have separated Northern Cape samples. Remember, we said OPLS is a model that focuses on maximum separation. So it pulled away the Northern Cape samples from the Western Cape samples as much as possible using the chemistry that it modeled. And the chemistry separating these two is 12%, which is for the first predictive component. However, orthogonal data, which was modeled, is 14.4%, which means the separation of samples in this direction, which is the positive and the negative there, is actually higher. The chemical differences within samples in the Western Cape province is actually quite significant when you look at separating Northern Cape samples from Western Cape samples. Okay. But so remember when I said we can investigate orthogonal variation separately. We can then go in and start looking at, okay, we have a lot of variation in our Western Cape samples. Could it be that in Western Cape they were picked from different locations and so forth? That we can also investigate separately. But for the purposes of the OPLS, you want to see why Northern Cape is different from the Western Cape. So because we have 2 groups, we can do a loadings plot, and we can also do an S plot. So I will show you the S plot. We go to Analyze, S plot. I will plot, I want to show this next to each other. So I close the other, and then I will tile them vertically. You remember the demonstration we got from the matrix S plot? The samples that are sitting on the right are correlated to variables that are going to be filtered out on the right of the S, which is the top right of the S. Samples on the blue, on the left, are correlated to variables this end. Okay, so in this case, the few variables, let me label them with retention time. These variables are high in these compounds that are occurring at that retention time. If you put your cursor on there, it shows you the retention time and the mass charge of every variable that is plotted here, of every loading there. So here you can see the retention time is still 4.7, but the mass is 291. Okay, the same applies here. With the blue, we don't have a lot of variables here. We have the 5.5, and this could be because we actually have clear separation here. So it means that there's so much variation between these that we can't find a lot of compounds that have clustered them together. So there's probably one that occurs in all of them, and the difference is probably just quantitative, and that's why you don't have a lot of variables. But the 5.5, you can clearly see that it probably occurs in your Western Cape samples more. Okay. Another plot that you can just use, if you go to your scores plot and then you highlight one cluster and then you do what we call a group to average comparison, you get a contribution plot, which just shows you, I'm going to label it. So the contribution plot shows you exactly what your S plot is showing you, the variables that are highly correlated in that group. Okay, this is something that we also use when we want to just confirm if we are picking the right number or the right variables. So the plots are interactive. If you highlight these variables here in your contribution plot, they'll also be highlighted. So if you go in and then you put some variables that are high risk, for instance, and then you go in and then you take all of that, your contribution plot will likely show you that, okay, these variables have a low contribution, perhaps you shouldn't pick them and you need to pick this one. Okay, so that's just a plot that we also use to confirm. The information that we that you need to report on in an OPLS, I mentioned you must show your score scatter plot. And once again, you can have a 3D score scatter plot for OPLS. But usually, in this case, we have two groups. So your T1 and your predictive and your T1 orthogonal are the ones that are important. So you can show your scores plot. You should also show your S plot. You can show a loadings plot if you have more than two groups. In this case, you also have, it will give you exactly the same variables, but the S plot is just a nicer way of presenting your variables. I will show you now. You can still see those variables that are correlated to your green samples and then the one variable for the blue samples. So, but what you can't do is to present an S plot and then you present a loadings plot because they're saying exactly the same thing. Okay, you report on your number of components as they are A plus 1 plus 3, and you mention what is the predictive component and how much of the chemical variation is explained in the predictive component, because this is what answers the question, what chemical difference is there between Northern Cape samples and your Western Cape samples. And then you can also mention the orthogonal and then the cumulative variation. We only modeled a small portion of our LCMS chromatographic data. The rest is not modeled. So it would be nicer if you can model more than 50%. Otherwise, the model is saying that a lot of your data is not really relevant. And then your Q squared here is very high. it's a 0.936, which means that the predictive ability of this model is actually very good. So this is essentially how you do PCA and OPLS. And I did mention that OPLS, like PLS models, they need to be validated. You need to test them. So ideally, you need to have a few samples that you leave out of your model, that once you have done this, you need to save this model as a test model, and then you introduce the few samples into this model, and where you know that you obtained samples from Northern Cape, so they must come and sit here, predicted to sit there, and then the samples from Western Cape must be predicted to sit there. So this is something that needs to be done for OPLS. In this case, I'll just do an internal prediction, not an external validation. So where you bring in new samples that you have information on is external validation. Where I'm going to do a 30%, 70% exclusion is internal. The Q-squared value, I did mention that it's a cross-validation parameter that we use to look at the predictive ability of the model. So this is good enough, but most reviewers would ask you to validate your model with another method, like your external samples. But okay, I'm going to just plot a new model quickly. In this case, I want to remove a few samples from the data set, and then I'm going to predict them back into the model. And then we see where they sit. This is not the ideal, but it's just a way of also assessing if your model is working. So we select, and then we do a random selection of 30% of the samples that we are going to exclude. And then you say, okay. I'll put the first two. We'll add a third one. And maybe a fourth one, only because in the previous model, we had 4 components. Otherwise, I would have auto-fitted. And then, yeah, okay, I think we can stop here. And then, so you'll see that now we have 178 samples because we excluded the other ones, but the other parameters are more or less the same. We do our scores plot. We just have less number of samples, okay? The other ones have been excluded. And then if you go to predict, and then you do a prediction plot, your samples, all your samples are now back into the plot. Now, I am going to label these samples with the province, but I will also color them according to the samples that were in the model and the ones that were in the predictions. Okay, so M3 means all the red samples are the ones that we use to create the model, and the blue ones are the 30% that we excluded. And the reason why I labeled them with the province is because I want to see if the predicted samples that are Western Cape are all sitting with the Western Cape samples, and all the Northern Cape samples are also sitting with the Northern Cape samples, which seems to be the case in this model. If you want to zoom in, you can just go to tools, and then you use the zoom, and then you can zoom into your data just to confirm if your blue samples are really Northern Cape samples. And then, yes, and then we can zoom out. We do the same with the Western Cape samples. You can see that most of them are sitting with the Western Cape samples. And then we can zoom out. So in essence, when your predictive ability of the model is actually high, the model that you develop is able to predict future samples or new samples or new classes of samples that come in. When your predictive ability is low, this is when it's very important to actually use an external data set. Even now with a high predictive ability, it's important to use an external data set where we bring in samples from Northern Cape and they have to sit together with Northern Cape samples. Otherwise, then we have modeled data, but our model is not trustworthy. Okay, so this is just to test and validate that the model that we've created actually works. Okay. Once again, everything else remains the same. We have the analysis advisor that you can also use, which I said can disappear for some of the plots. Yeah, but yes, we can. One more item that I can just show you. When you are using Simca plots for publication of a thesis, you can right click on your plots and go to format plot. Format plot helps you to change a lot of things. The labeling, remove grid lines, put a background and so forth. This is always a problem with the quality of the images that the software produces. They'll always ask you, okay, make your labels bigger or make the font bigger and so forth. So you can come here and then you are able to change most of these things there. Okay. Yes, and then you can save your data, your project, and then you can always come back to it at a later stage. Simca plots, you can copy it. There's the original size, different sizes, depending on what you want to use it for presentation, or just, you can put it in PowerPoint. You can, for publication purposes as well, you can adjust all of these. You have bitmap and all the different formats, and then print quality can also be adjusted over there. So you can copy your images and send it to PowerPoint or to image, to MS Word. And the other thing that you can do is you can add this to a report. You can create a report in Simca, which is something like this. Already this plot has been added to a report. This is something that you definitely, maybe you just want to use it for your own internal reporting purposes, but for publication, you would want to remove a lot of the content and probably make some font larger and so forth. But Simca generates a report, and it's entirely up to you to choose what plots you want to send onto the report. You just add to the report, and then you have a second one, and so forth. Spectral filters, once again, we have spectral filters that you can use depending on the data sets that you have. And then, yes, and then, yeah, that is it. And then one more item. If you click on data set, it takes you to the original data that you entered. So if, for instance, there's a problem with one of the labeling, you can always come back here, change the label, save the data, and then see if the software picks it up and changes in your score plot. If it doesn't, then you must go back and then you close the software and then you must reopen it. Then automatically it updates. Okay. Thank you very much. I think this is all that I just wanted to demonstrate this afternoon. I want to thank my colleagues in the Phytomedicine Research Group and Professor Viljoen for giving me this opportunity. The NRF chair that I work very closely with. I want to thank the department and TUT for, yes, acquiring this software for us, which is, yeah, it's a licensed software, and we use it here extensively for our research. And thank you to the organizers of the workshop for allowing me this opportunity. Thank you for listening.
Thank you so much, Maxleene. That was amazing. I guess you've answered the question from Alisa about, no, not Alisa, but Betty. How do I get the software, and can you please share link? So you said it's licensed.
Yes, it is.
Okay. So are you willing to share the cost of a license, or you're not aware of it, or it will be on the website?
I checked actually before I came for this. It's not on the website now because they have different packages now of the software. So I suppose depending on what you want to use it for, then they will be able to provide you with a code. But it's a Umetrics software. If you go to their website, you can request that information. They will be able to send it to you.
Okay, okay. Apparently you can get free versions online, even though you might want to be careful. But thank you for that.
Yes.
Yes, I guess they're probably limited as well in what you can do, or exporting data and all that. That's how they usually limit these things.
Yes, Molati, just about the SIMCA software, you can get a demo version that you can use, I think, for 2 weeks or for a month. Okay. And then after that, then you need to buy. Okay, okay.
Thank you for that. There is also a comment there. Thank you very much for the concise and informative presentation. Extremely useful. I thought that was very comprehensive. Thank you very much. Any more questions or comments, please? Nothing in the chat just yet. Okay, thank you so much. Should we maybe start the combined Q&A sessions in case some questions came up, or other general things? You know, the unfortunate thing about doing things online is we miss out on the tea breaks and the lunch, where people could approach each other and ask other questions that may be outside the scope of what we're doing today. How are you open to people reaching out for collaborations and training, additional training that makes sense in your group?
Yes, definitely.
Okay. So if anyone would like to make contact, please feel free to contact us. We'll make sure we contact you with any of the speakers that we had today in case you need clarification, or if you'd like to collaborate, or if you need clarification on what was said today, or even beyond that, the research that they're currently involved in. Any questions for Maxleene, Marie, or Vilma today? It has been a long day, so I'm sure everyone is tired now. Okay, while we wait for questions and comments, I would like to thank Marie, Vilma, and Maxleene for giving us great talks today. We are very much appreciative of how long these things take to prepare, and actually how hard it is to move the whole day to be able to give these sort of talks. But I'm sure we reached a high number of people to that. The highest I think was at 85 people that had joined to the meeting. So I'm hoping even if half of the people that came to the benefited, then we're definitely on the right path. Please look out for future MSA ACGT events, workshops. There will be more workshops this year. I think there's about 2 scheduled. Dates will be communicated. There is a very interesting journal club that happens every week that's run by Dr. Mason, which is a mixture of introductory lectures and some student presentations. And so far it's been going very, very well. Please contact us if you'd like to be put on the mailing list so that you get links and flyers for those. Those I'm not sure if there will be one next week, but please look out for communications. Those have been going very well, and I think they're picking up momentum nicely. But there will be 2 or 3 other workshops. There's an advanced one later. There will be a more personalized one soon. thank you everyone who participated in putting this together. And thank you to all the participants that also came. We understand that a day is an expensive thing to put aside, but we're very appreciative that you joined. No comments. Thank you, Maxleene, very informative. Yes, I think that's the general thing, that everyone is taking something away from today. And I hope that if you are new to metabolomics, it's giving you some check boxes with your experimental design. And if you're already doing something, there's some things that you can fix with your analysis and your approaches to some of these techniques and choosing models and ideas on how to approach that. Do any of our speakers want to say anything before we close the session?
Thank you, Mulati, for giving us the opportunity and all the students the chance, the opportunity to be able to get more information on. And I know the students have a big problem on, especially the modeling and what has to be reported and what must be in an article. And I think Maxleene gave us a very good overview of that. But thank you for Metabolomics South Africa to give us the opportunity and the students the opportunity.
Thank you so much for that. All right. We'll be in touch about the links to the surveys I mentioned. We'll try and share the links to the recordings as well. And anyone who still wants to join MSA, we'll send the link for the registration for all of that. But yeah, I think we can safely close the session for today. Thank you, everyone.
Thank you, Mulati.
Thank you, Mulati. Goodbye.
Bye.